Okay, so thanks for coming to this session. I'm Vandy Berten from the research department of company Smals. In this presentation, I'm going to share my experience about fraud detection in the social security sector using network analytics technique and graph databases. So this is going to be the outline of my presentation. After having introduced the context of graph and graph databases with some comparison to the classical RDBMS model, I will explain a business problem in the context of social dumping, and we will see how this problem can be translated in a graph problem. Okay, so first of all, we need to understand what's a graph. Well, we can see our world as composite of entity, a person, a company, a building, a computer. All of those entities have a physical reality, but we could also have entities that have more like conceptual reality, like a software program, or a package, or a group of persons, like a political party. Well, so those are entities, but first of all, there are relationships between those entities. This person is a friend of another person. This person is the boss of another one. This person works in a company that sells houses. This person owns a house, is the developer of a package, of a program that depends upon another package that runs on a server, and so on. So all of those are relationship between entities. The classical database system, the RDBMS model, mainly focus on entities. But by putting the focus on the relationships and not the entity, a whole new family of analyses are possible. And this is what we are going to do with network analytic and graph databases. So this is what we call a graph or network, and sometimes we talk about a social graph or social network because there are people, some of the entities are people. Okay, so this kind of model where nodes represent people or companies or group of places has been shown to be really efficient in the context of fraud or criminal behavior detection, as well for many other use cases. But the problem is that, as we will see in the following slides, the classical RDBMS model like Oracle, MySQL, Postgre, and so on are not good at all for storing and creating a graph structure, both in terms of execution performance as in terms of expressiveness of the querying language, which is usually SQL. This is why graph database has been introduced, putting the focus on relationship instead of entities for RDBMS. Okay, let's talk a little bit more about graph database. But before talking about graph database, I will first talk a little bit about the RDBMS model and the way relationships are implemented in the RDBMS model. So let's assume that we want to represent the relationship between workers and companies. And we choose for that classical RDBMS like MySQL, Oracle, or whatever. And we first consider the simple case where a worker can only work for one single company. A classical model for doing that would be to have two tables, one for workers and one for companies, and using a foreign key in the table workers to point to some primary key in the company's table. If we need to get the list of employees of a given company, for instance, Smals, we'll write a SQL query like this, where we select a field in the table workers. We put some code with join to say how the two tables are linked together, and then we say that the company is Smals. In this request, we have two parts somehow. We have the part that is really want to know, that concerns the developer. He wants to get the name and he wants the company to be Smals. Everything that is put together is how the relationships are implemented in the database. But this part does only depend of the model and should not depend. It should not change between requests. Somehow we may say that this part should be the DBA's responsibility, or at least the data modeler responsibility. Note that there are no difference between the field employee ID and the field name from the database point of view, apart from the interpretation we give to him. Okay. Let us make the thing a little bit more complex and consider now that a worker can work for several companies at the same time or not. What we usually do is that we create what we call a join table, which contains foreign keys toward the primary key of the two table workers and company. Again, if we want to get the list of all the employees of company Smals, we need to write something like this with, well, still the same part that we want to know, and in the middle, everything that explains how the relationships are implemented. We need to join here because we have two foreign keys. Okay, let's consider another model where we have here something more like a social network, I would say, with people liking or following or depending upon or knowing or whatever each other. And we consider for this a table people with all those people, and then the table, for instance, lag with in each record a foreign key, well, two foreign keys towards the table people. If in this model we want to know who, for instance, Bob liked, we need to do this kind of request with twice the table people, once for Bob and once for the people that Bob likes. Sorry, again, what we want to know is the name of the people and that the first people is Bob. Everything in the middle is how the relationships are implemented. If we want to just go one step further and saying who like the people that Bob like, so we Bob likes square. That's a question that is really common in a recommendation system. For instance, Facebook will recommend you to be friends with a friend of your friends, or eBay will recommend you to buy a product that has been bought by people that bought the same product as you. Well, for that, we need to write this kind of code with twice the table people, twice the table likes. And for a really simple question, it becomes really complex it becomes a really complex query, difficult to write, difficult to read, difficult to understand, difficult to maintain, and so on. Of course, in some database system like Oracle, there is a mechanism connect by, for those who know that simplifies a little bit the query, but the execution is still quite heavy. So to resume the way relationship between entities are implemented in RDBMS database. In the case of one-to-one relationship, the relationship between entities is modeled by somehow distorting the role of an attribute. We do not have a key type. We need to choose in any kind of standard type like integer, whatever, to have this key. And if in the M2N relationship, we need to somehow distort the role of a table. So there are tables representing entities, there are tables representing relationship, but there is no way to distinguish those tables from the database point of view. We may say that in RDBMS, the relationships are not presented in the DB itself, but in the queries. Also, the join mechanism is something really heavy in execution time. We first need to... where's my pointer? Oh, okay. We first need to find the right company here, the right ID here, and then you need to... and for this, you need to look through this table using some kind of index. Then for those indexes, you need to go through this table, again using indexes. And for all the IDs you find here, you need to go through this table, again using index to find the list. That's something really heavy in execution time. Okay, so with the growing need of storing all kind of data to solve all kind of problems, well, RDBMS are not anymore the universal solution, we may say. And because of that, a new Wolf database family has raised in the recent years that we call NoSQL or NoSQL solution. I'm not going to talk too much about those NoSQL solutions, but there are mainly four families of NoSQL. the key value, column, document store, and graph database. In my presentation here, I'm going to talk about this last family, the graph database family, showing some example with the market leader in graph database, which is Neo4j. Okay, done. In a graph database, we do not consider and we do not store tables anymore, but we store entities and relationships. For instance, here we have four entities that represent some things, I would say. Those entities have attributes or properties, so a key and a value. The key name has the value, for instance, Smals or John or so on. And those nodes have also a label of a type. So the two blue nodes are of type people. That means that they represent people. There is a node company. There is a node address, and so on. Okay, so those are the entities, and we have also a relationship between those entities that again could have labels and attributes. So in this model, I may say that I have a person whose name is John that works for the company Smals, who is friend with Bob, and this Bob lives at a given address. In a graph database, those relationships are going to be stored like pointers. That means that in a node, we'll have the physical address of all the nodes that are pointing by the relationships. Well, the graph databases have mainly two objectives. The first objective is to split apart the relationship definition, how the relationships are implemented. That should be done at the creation time of the database, and the matching those. So the querying should not take care about those relationship definition. That's one side, and the other side is to have a really fast mechanism to traverse relationships, not using the join mechanism, which is known to be really heavy in execution time. Just to give a small example of how should like a graph database query in this example. So this is the code I needed to use to know who are the people who like the people that Bob likes in SQL, and if I translate this in Neo4j, in Cypher, which is the language of Neo4j, I will need to write something like this. I will need to match a node of type people whose attribute name is Bob with a relationship to another node of type people, relationship of length 2 of type like. So I'll come back later to this kind of queries. Well, just to give another example how shorter the code could be in Neo4j, this is the code the MySQL code that was used by a client of Neo4j before they switched to Neo4j, and this is how they translate the query in the Neo4j. So much shorter, but also much easier to understand, to read. I said you a little bit earlier that the graph database could be really good for the recommendation system, and eBay uses Neo4j for their recommendation system. They say in some report that thanks to Neo4j, they've been able to do things thousands of times faster with queries that requires 10 to 100 times less code. Okay, so this Neo4j. So Neo4j is the current graph database leader. That's a company that is 10 years old now. The engine is written in Java. It's then multi-platform. They propose two editions, a free edition and an enterprise edition. The two are open source. Of course, we can query this database from any kind of language. It's from the consistency point of view that they are ACID compliant, and the database can be created through Cypher, their own language, or Gremlin, which is a more standard language to graph database. Okay, now let's look a little bit more how we can build a request, and we'll consider for that the same example as in our introduction with the list of employees of a given company. In this case, we will have two kinds of nodes, a worker node and a company node, and one type of relationship works for in my example. So what we need to find is all the paths with a worker connected to relationships through a works for relationship to a company node whose attribute name equals Smals. And this is somehow exactly what we are going to write in the Cypher language. I want to find a worker node connected via works for relationship to a company node whose attribute name is equal to Smals. And for each time I find this pattern in the database, I will return the name, the attribute name of the worker, the birthday attribute of the worker, and the start date of the relationship. Okay, so the parentheses mean a node. After the two dots, that means the label of the node. Okay, so node of type worker, node of type company, and the arrow with the brackets in the middle means a relationship of type works for. I can even write this a little bit shorter by putting the constraint, the where constraint in the node here. So this means that I want to match a node with the parenthesis of type company whose attribute name is equal to Smals. Then I don't need anymore the where part in my request. Okay, so if you compare the way it works in the two systems, as I said before, in the RDBMS model, to find all the people that works in a given company, we first need to go through this table through an index, which is going to have a logarithmic complexity. And then from this, we need to go through this table, again, logarithmic complexity, and then to this table with the index logarithmic complexity. With the graph database, what we are going to do is that, of course, we first need to go through an index to find the node that attribute name is Smals, but that from this node, we have the database contains the list of pointers towards all the neighbors of these nodes. So that means that following, we just need to follow pointers. It's going to be a constant complexity. Okay, so, well, as you may know, Smals, my company works for a public institution in Belgium. And in this context, my team supports the National Office for Social Security in fraud detection, mainly related to what we call social dumping. So the social dumping is when a foreign company send low-cost workers in other countries, in our case, in Belgium. This is something that is allowed by Europe, but it has been done in a strict framework that the National Office for Social Security is in charge of controlling. I will first present two declarations that have been filled by companies and then the underlying database structure, and then we'll see the kind of pattern we may need to find. So my company has developed those two applications, is in charge of maintaining those applications, and we are doing data mining of those data. So the production applications are in a classical RDBMS model, Oracle mainly, and then in order to do data science and data mining, we export the data from those RDBMS database to a Neo4j database. So the first application we need to consider is Limosa. So Limosa has to be filled when a foreign company that we call the sender wants to send out workers in Belgium. So in this case, this company needs to declare who is going to work, so the worker, for which company this worker is going to work, and where this worker is going to work. The where part is what we call the place of work. The place of work. So it could be either an address, the physical address, like a building address or whatever, but it could also be in some case a company. Then in our model, a declaration is a node with links to the employer or the sender, a link to the worker, a link to the client, and a link to the place of work. And if in the case this place of work is a company, we have an additional link between this place of work and the company. Okay, so this is the model, or data mining model, I would say, but not the production model, which is a little bit different. Okay, so Limosa, when foreign worker come to Belgium, another declaration that is needed is on big working sites. There are often many companies working together. They are usually organized in a sort of hierarchy. We have a main entrepreneur that asks some other company to work for them on a given work site, and those companies ask other company to work for them, and so on. Then we say that a company has a subcontractor on a given work site, and this is something that has to be declared in the DDT application for déclaration de travaux in French. So in our graph model, a DDT declaration node says that on a given work site that we call DDT POW, place of work here, some contractor company has a subcontractor. And of course, on big working site, we do not have only two companies working together. We have many companies. And in this case, we could have this kind of declaration saying that on a place of work, on a working site, POW here in purple, a main contractor A has two subcontractors, B and C, and the C company has another subcontractor, D. Okay. Then we can combine those two kinds of declaration. If a foreign company sends out workers in Belgium to work on some big work sites, we'll find data in the two databases. In Limosa, because that's a foreign company that sends people, and in DDT, because that's on a big working site. So the control service we are working for is interested in several kinds of patterns, and we have here an example of such pattern. So for some legal reason, I won't detail too much here. If a foreign company A sends out workers to a client B, so if a foreign company A sends out worker to a client B to work on a given work site which is given by a company, that's in Limosa, and if this C is declared as this company B is declared as the subcontractor of this company C on some big site, then for some legal reason, A should also be declared as a subcontractor of someone on this big site. Okay, well, that's the constraint. That means that if we can find such a pattern here, so the circle here, if we find this, then we need to find this path below. If we don't find this, there's something wrong that should be investigated by the control service. So this main loop can be expressed in the cipher quite easily. So this is the Limosa part, the part of foreign company that send out people in Belgium, and this is the subcontractor part, so the DDT part. Okay, so the main loop can be expressed in cipher this way. So a company A is linked to a Limosa declaration here, which is linked to a Limosa place of work here, which is linked to company C, and so on, and then back to Limosa declaration. Okay, so that's how we need to write this in the cipher query. And then the part below that should not exist is at least that part below that should exist. But if it does not exist, we need to report it. It's expressed this way. So A related to some DDT declaration node here related to this DDT place of work. Okay, so the full query look like this. So well, this is exactly what I've just shown before. The where is the not existing part here. And what I want to return from this is to return all the triplets of company ABC that fulfills this query. So we have the main loop, but we do not have the path below. And for those three companies, I need to run how many Limosa declaration in how many Limosa declaration disappear, and in how many DDT declaration in this appears. Okay. Well, so we have copied a lot of data from our the production system to our Neo4j database. That's more or less, well, 20 million of nodes and 45 million of relationship. We have nodes, we have companies, we have declaration, we have a duplication group I'll talk about later, we have addresses and so on. So that means many kind of labels, many kind of relationships and so on. From this database with a graph, with a cipher query, the cipher query I just shown before, it took me a little more or less 10 seconds to get 300 results. And I'll switch to this now, almost. Sorry. Okay, so this is Neo4j browser. The Neo4j browser is the web interface that is provided with Neo4j. I can see that here that I have many kind of nodes. For instance, I can click here to get a sample of Limosa declaration nodes. So those are nodes. If I double click on a node, this says me that this declaration says that this work. So all the data you'll see are anonymized, randomized, so there are no sensitive data here. So this worker works for this company, and in this case, the client and the employee are the same. It should not usually be the case. Okay, here we have a client. So the Belgian client here, the foreign employee here, and the worker here. In this case, there is no place of work. It could happen many different kind of situation. Okay. Okay, so now I can run the query I've just shown you before, and a shorter version of this query that just gives me back one result. So this is my foreign company with this random name. This is the Belgian client, the place of work, and the subcontractor relationship between the two. Okay, and from my request, I know that I should not have any path from this place of work here to this foreign company here, and I can here double click here to expand this place of work. So on this place of work, there are 3 DDT declarations. I can expand them, and I see that indeed I don't have any relationship from this place of work to this, and this is not really normal, and that means that this is the kind of situation that the control service need to deeper investigate. Okay. So I got this result in less than 1 second on the database with 24 million node, 45 million relationship on a not that big server, a more normal server. Okay, and if I run the query that gives me the full table of results, it should take about maybe 10 seconds. Well, I run it a little bit before here. It's gonna be faster. Okay, so this says me that this company has the A, so the foreign employee, the foreign company, the Belgian client, and the place of work here are present in almost 300 Limosa declaration and 70 DDT declaration without having this this part that should exist. So that's really the kind of company that is problematic, because very often they forget to declare the relationship between the foreign company on the website. Okay. Well, if I should have done that in a classical SQL or RDBMS model, we need to realize that any node or any relationship corresponds to a record. So I should have more or less 65 millions of records, and any label of any type usually corresponds to a table. So I have more or less 24 table. And in my Cypher query, any relationship I have between two nodes, relationship between a node of type 1 and type 2 relationship of type 1 corresponds to a double join with this as a join table. That means that my query from before will contain something like 20 joins, 20 SQL joins. On the 20 SQL joins on a database with 65 million records, it's, well, in many cases, something that will not take 10 seconds to run for sure. That would be far more complex to write, to read, to understand, and to maintain, and much longer to run. Okay. Well, this would work, what I've told before, if the company are declared the same way in my two databases, in the Limosa database and DDT database. The same way would mean with the same official ID, the same official company ID. Every company has an official employer ID or company ID that should be used in the two databases to be able to map them to the same company. The problem is that in some databases, mainly for foreign company, that is not mandatory at all to use the official ID. So just giving the name and the address of the Belgian client of the foreign company is enough. And with this, that's quite difficult to map them together, to realize that that have the same company. We have in the database some company that appear in more than 1,000 times with different IDs, but exactly the same company. That they just give the name 1,000 times without giving the company. And then in the production database, they are considered as 1,000 different companies. So we need to deal with this to be able to do data mining on the data. So the first step in our duplication management is to identify all the company nodes having the same name or almost the same name. In this example, we are showing 3 company nodes that have, after being standardized, the same name. So by standardized, I mean putting everything in uppercase or lowercase, removing all the alphanumeric characters like dots and so on, and also removing all the legal forms like ASBL, VZW, SA, and so on. So once we have found a group of nodes with almost the same name for after cleansing, we create what we call a duplication group node here in the middle that links them all together. So that means that from this node, that's in the database, in the graph database, that's quite easy to find other nodes that have the same name or almost the same name, using just cleansing technique or using more complex technique like Levenstein distance and so on. But of course, having the same name does not mean to be the same company. We need to use some more information. This is something that could be done using data quality tools like Trillium, for instance, or OpenRefine for open version of this. It could also be done in Python or R, whatever, but usually that's more efficient in tools that are made for that. Okay, an additional information we could use could, for instance, be addresses. So we have address information in many databases. but the main problem is addresses is also the data quality. So, for instance, the node Avenue Fonsny sometimes is written av.fonsny, sometimes Avenue Fonsny, sometimes Fonsnylaan in Netherlands, in Dutch. So that means that before doing anything with addresses, we need again to standardize those to put the same address that should be written the same way everywhere in the database. So that's again something we need. We need professional tools to do that. Professional tools that have a knowledge base to really able to do good matching. So here my graph structure says that on Avenue Fonsny on number 37 there is the company Data Allowed. On number 20 there is the company Smals, and Smals is also on Quai de Willebroek on number 38 in Brussels. Okay, so a node here is a street and not an address, but that's a choice you've made that allows us to be a little bit more flexible in our analysis, and of course to have far less nodes in the database. Okay, so we can now put those things together now and replace in any query, any node we could replace any node we want to split by this kind of diamond, with in one side A1 corresponding to the company node declared in one database, and the one source database, and A2 corresponding to the company node declared in the other database. For instance, A1 in the DDT and A2 in Limosa in our case. So with this, we make sure that A1 and A2 have almost the same name or exactly the same name according to some constraints we could give on this duplication group name, and also they share the same street. If we want to make sure that they have the exact same address, we need to put some additional constraints on the label here, because we put the number in the street in the relationships. Okay, that means that if I want to consider that the company B is split, so the Belgian client is split into duplicates, that's quite easy to modify the schema and then to adapt the query. Well, we may know that a classical approach to process duplicates in database is to merge the duplicates into a preprocessing phase by applying some rules. For instance, we may say that if the name of two records is the same and the city is the same, then we merge those two records, as well as if the name is almost the same and the address is the complete address is exactly the same, then we merge those. But in our approach adapted to graph database, it allows us to keep some flexibility. The idea is that we could, for instance, want to be really sure that B1 and B2 are the same company, but we could be a little bit more flexible by splitting A into two companies, accepting just that have the same name, and we do not care about the address. I have an example here, just need to swap to here. Well, I run this example a little bit earlier because it's a little bit longer than 10 seconds to run this. Sorry, where is it? So this is an example where the B node, so the C node, sorry, the place of work is split in two. So we have one node which is declared as the parent, the contractor of the relationship here. We have another node which is declared as the place of work on this relationship, but we know that they have almost the same name here, thanks to this duplication node, and also that those two company nodes share the same address. So we may think that they are actually the same company here. That was not found before with the other, the first query, that the simple query, I would say. Okay, so this will conclude my presentation. So from my personal experience, not only my personal experience, the personal experience of many people, graph databases are really a really good partner for fraud detection problems. From many point of view, they outperform RDBMS, and from the expressiveness point of view, from the execution speed, point of view, for this kind of problem, of course, for problem where we really have a relationship between entities. This is going to be only efficient if the data quality is properly taken into consideration in the model, at least if the data quality is not really good, but that's really often the case for a big database. We have applied it for fraud detection, but that's far not only the only application domain. Like I've talked about recommendation system, infrastructure management, master data management, intelligence, and so on. That are all many sectors where graph databases are really interesting to consider. I put some references here on the website smalsresearch.be. I've put the slide of my presentation here. I've put also some blogs in French that I've written on this subject. Here are some books references about graph database and also the fraud detection in using graph database. And thank you for listening. If you have any question, I'll be happy to take them now, a little bit after. I'll stay a little bit at the Smals stand in the big area down there. Thanks a lot.